welcome back to my YouTube channel. We are going to be looking at Sturm liouville equation. So please I beg you guys, please do so well to subscribe on my videos, subscribe on my channel, like, and at least drop a comment after watching the video if you like it. So we're going to be looking at Sturm liouville system. So under Sturm liouville system, we're going to be looking at Sturm liouville equation and Sturm liouville and the arbitrary constant. So what is Sturm liouville system? Sturm liouville system is just a system of equation and conditions and boundary conditions which helps us to look for what's called eigenvalues and eigenfunction. I'm going to repeat myself. Sturm liouville system consists of Sturm liouville equation and a boundary condition which helps us to find the eigenvalues and the eigenfunction of that boundary condition. So, what is a Sturm liouville equation? So let me call it SLE, Sturm liouville equation. So the Sturm liouville equation is giving us the derivative with respect to x of p dx times dy dx plus q as a function of s plus lambda rs from bracket y equals close bracket y equals 0. So this is the Sturm liouville equation. So now, and I said there's what we call boundary conditions, right? So now let's assume this is my boundary condition where alpha 1 y as a function of a times y as a function of a plus alpha 2 times y as a function of a prime is equal to 0. Now this is when x is equal to a, and we have beta 1 y as a function of b plus beta 2 y as a function of y as a function of b prime equals 0. This is when x is equals to b. Right, so this is what I call my boundary condition. So together with this equation and my boundary condition where s is equal to a, b, I have what is called the Sturm liouville problem. So together with my equation and my boundary condition, I have what is called the Sturm liouville problem. So like I said, the Sturm liouville problem is the combination of the Sturm liouville equation and the boundary condition, in which from there we'll be asked to find the eigenvalues and the eigenfunction. So now let me explain what eigenvalues are. Eigenvalues are just like when we are given a particular equation. For example, if you can remember our first order and second order, well, if you can remember our second order differential equation, in which we'll be given a particular equation, then we use arbitrary solutions to solve. Eigenvalues are those values that we assume that, for example, so values in which we tend to give a particular range which helps us to solve the equation solve the Sturm liouville problem given, then we get our eigenfunction. Well, let's just do something. So now, for example, if you are asked to solve a Sturm liouville problem, you'll be given an equation. Let me start from there. So if you have to solve a Sturm liouville problem, you'll be given an equation. So let me just take an example for you to understand. Now, before I proceed, if you solve a Sturm liouville problem, and like I said, in a Sturm liouville system, we'll be asked to find the eigenvalues and the eigenfunction. Right, so we have to find the eigenvalues and the eigenfunction. The eigenvalues is represented as lambda, and the eigenfunctions are mostly represented as y. Right, so if you finish solving a Sturm liouville problem and you have that your eigenfunction, which is y, is equal to 0, this function here is called a trivial solution. Now, when you solve your second order equation, for example, your second order equation usually gives us mostly a quadratic equation. So after solving it, you'll be having something like this: a solution of y, which we have something like this: c1 raised to power x of y, let's say alpha x plus c2 raised to power beta x. This is a standard solution for second order differential equation. So for example, now when you finish solving that equation and you have that y is equal to 0, we call it a trivial solution, right? So now let's just take an example. So Sturm-Liouville equation is trying to get the eigenvalues for which we will not obtain a trivial solution. You see, that's all about Sturm-Liouville equation. Like I repeat myself, Sturm-Liouville equation is obtaining the eigenvalues in which we will not have a trivial solution. So we call that a non-trivial solution. So now let's take for example. We are given this equation equals 0. Now, like I said, you'll be given a Sturm-Liouville equation. Now, how do we know this is a Sturm-Liouville equation? You'll be having a lambda there. Just like our general form of Sturm-Liouville equation, we're having this is, if I try to open this, I'm going to be having p prime x, and differentiating this, I'm going to be having a second order differential equation which matches perfectly with the equation given, which is this, right? Now we're having a q of x here multiplied by y, and we're having a lambda of x, lambda times y times rx, which fits perfectly to this. So this is a Sturm-Liouville equation. So now we'll be given a boundary condition. Like I said, we'll be given a boundary condition. For example, you are given boundary condition of where y as a function of 0 is equal to y as a function of L. Let's use a number. Y is a function of 5, and they are all equal to 0, right? So this means right here that y as a function of 0 is equal to 0, and when y is a function of 5 is equal to 5. This means when x is equal to 0, y is 0, and this means when x is equal to 5, y is 5. That's that. So this here is the boundary condition, and this here is the Sturm-Liouville equation, which together gives us a Sturm-Liouville problem, SLP. So now, how do we solve this? So now we're going to be finding the eigenvalues and the eigenfunction, like I said. So to get the eigenvalues and the eigenfunction, we are going to be assuming some certain values of my lambda here. So what do I mean? So in order to find the eigenvalues, we must consider different cases of our lambda here. Now we're going to consider the three cases mostly considered in a Sturm-Liouville equation. Now follow me step by step, because you use the steps in solving almost all questions of Sturm-Liouville system. So the three cases used in solving a Sturm-Liouville problem are mostly when lambda is equal to 0, when lambda is greater than 0, and when lambda is less than 0. So these are the three cases we will be considering. So if we will consider for when lambda is equal to 0, consider for when lambda is greater than 0, and consider for when lambda is less than 0. So we are trying to get the eigenvalues for which, when we solve for when lambda is equal to 0 and we did not have a trivial solution, then that the eigenvalues you have there, that is our eigenvalues. So when we solve for this and we have a trivial solution, that is y is equal to 0, we will not make use of that. We'll say it's a trivial solution. When we solve this and we have the eigenfunction y to be equal to 0, we say it's also a trivial solution. But when we solve this too and we have it, but y is not equal to 0, then we say we collect the eigenvalues and write down the functions. So now let's proceed. So we're going to consider in our first scenario right here, for which lambda is equal to 0. This is case 1, right? So taking this is our equation, right? Now taking this equation, just substituting it when lambda is equal to 0, we'll be having y double prime is equal to 0, right? So now I assume this is my equation, my second order equation, right? This is, remember, this is also equal to this, the square y, the x square is equal to 0, right? So I assume this is my second order equation. So now let me represent it in form of auxiliary equation. If you can remember what auxiliary equation is, if you have a second order differential equation as this, an auxiliary equation will be given as m square plus m plus am square plus pm square plus c equals 0. This is an auxiliary equation, right? Hope you have not forgotten. So looking at the y double prime there, my auxiliary equation will be given as m square equals 0, right? So now, like I give, like, if you can remember the standard solution to second order equation, in which you'll be having something like this: y is equal to c1 exponential alpha x plus c2 exponential beta x. So this is a standard solution to second order differential equation. So if I take the square both sides of m, m is equal to plus or minus square root of 0, right? So which means m1 is 0 and m2 is also what? 0, right? So since we're having two solutions that are the same, if you can remember the rule that applies for second order differential equation, we'll be having my solution will be y is equal to c1 exponential. Now since this right here, remember, this is also my alpha 1 and this is also my beta 1, right? The solutions we get here is what we'll fix here, right? So my m1, which is, now since I'm having two the same solution, I'll be having c1 m1 x plus x times c2 m2 x, because I'm having two equal solutions, right? That's why I'm adding x here, right? So now let's solve this properly. We'll be having, since m1 is 0, we'll be having c1 plus x. Now since m2 is also 0, we'll be having what? c2. So we have the solution right here. So now let's check, because we are not true actually. So we try to get the values of c1 and c2, right, to prove or to know if it is a trivial solution. So if c1 is equal to 0 and c2 is equal to 0, then it is a trivial solution. Then we will not be able to get our eigenvalues, right? But when it is not equal to 0, we can get our eigenvalues. So now let's proceed. So now let's proceed. So what next? If you can remember our boundary condition, we were given y as function of 0 is equal to 0, and we're also given y as function of 5 is equal to 0. So now, which means that when x is equal to 0, y is 0, and x equals to 5, y is also 0. So now let's substitute. So we'll be having y when x equal to 0, we'll be having something like this, right? Then y is equal to c1, right? Then we move to when y is equal to 5, when x is equal to 5, right? And since when x is equal to 0, y is equal to c1, right? And since when x is equal to 0, y is equal to 0, that means c1 is equal to 0. You understand? We're having y as a function of 0 is equal to 0, right? Meaning that when y is equal to 0, when x is equal to 0. And this is our equation y, right? So this means that when I put the values of x to be equal to 0, y is equal to 0. And since y is equal to 0, c1 is equal to 0. So we've gotten the value of c1. So now you try the second boundary condition, which says when x is equal to 5, right? So since c1 is 0, we're having 0 plus 5 c2, right? And since they said y is a function of 5 is also equal to 0, that means all this is also equal to 0. So we're having 5 c2 is equal to 0, which means c2 is also equal to 0. So if I go back to the equation y, I have, for which I have c1 plus x c2. If I put my value of c1 and c2, y is equal to 0. So since y is equal to 0, like you can remember, this is a trivial solution. Right, so we are not making use of this. So it takes for our second case, right? So I hope you are really following me. So the second case says when lambda is less than 0. So from our original equation, you have y double prime plus lambda equals lambda y equals 0, right? This is from our original equation we were given in question. So now when lambda is equal to 0, when lambda is less than 0, meaning that lambda is going to be negative, right? So now let's put it here. So we'll be having y double prime minus lambda and y equals 0, right? So now let's solve this using our second order form of equation, right? So using second order method of auxiliary equation, this becomes m2 minus lambda equals 0. And if you can remember from our second order differential equation in which we have this, remember this can also be written as this, right? Right. So if you can remember our second order equation, which is of this form, this d square y dx square minus n square y is equal to 0. Our solution will be y equals c1 cos nx plus c2 sine nx. So this is the standard solution for a second order equation that is of this form. So if I compare this to this my equation right here, my lambda is equal to n square, right? Which makes n to be equal to my square root of lambda, right? So now let's move on. Let's continue back with the equation. So we'll be having m square equals n equals lambda, right? So square root in both sides. My m is equal to plus or minus square root of lambda, which means my m1 is equal to square root of lambda and my m2 is equal to minus square root of lambda, right? So then we can put it back into our general solution. Remember, the general form of solution is this, right? So we can put it back into our general solution, and remember I said my n is equal to this, right? So you can put it back into my general solution, and we have y equals c1 cos, and since my n is equal to square root of lambda, just put square root of lambda x plus c2 sine n is also square root of lambda, but in this case I don't need my second solution, because I only need to know that n is equal to the square root of lambda. I actually didn't have to even solve all this. I just needed to just input it back into my solution. I actually didn't have to solve this. So we only need this, right? We don't actually need this. So we only need n to be root of lambda. So we put it here also. N is equal to square root of lambda. We have a square root of lambda x. So this is my solution. So remember, we're trying to get eigenvalues, right? So now first we need to prove, or we are trying to get the solution in which we are going to try to get a non-trivial solution, right? A non-trivial solution when y is equal to 0, and y can be 0 if c1 is equal to 0 and c2 is equal to 0. So when c2 and c1 are both 0, it gives a non-trivial solution. So now let's proceed. So from our boundary condition that says y, which is a function of 0, is equal to 0, and y is a function of 5 is also equal to 5, then we put it here, which means s is equal to 0 and here is x is equal to 5, right? So we put it into the equation we have. When s is equal to 0 here, 0 times this, which officially is also 0, and because 0 is 1, right? So we'll be having y is equal to c1 plus, when I put x is equal to 0, all this becomes 0, and this is cos, not cos. And remember, cos 0 is also 1. So when I put it here also, sine 0 is 0, then which makes it 0. So my y is equal to c1, right? Then I apply my second boundary condition from when x is equals to 5. Then when I put, remember I already have c1, right? C1 is y is equal to c1. So I put when x is equals to 5 here. So this is 5. I've not finished solving this, right? So y is equal to c1. And remember, when x is equal to 0, y is equal to 0. So which means c1 is also equal to 0. So technically, all this becomes 0, right? c1 is 0, all that becomes 0. So I'll only be working with this, my second side. So I'll be having c2 shine lambda x. So when x is equals to 5 times this, right? So I'm having a valid solution right here. This is c2 shine lambda x times 5. So I'm having something like this, right? So in order for now, remember, we don't know if this is a trivial solution yet, but we know that c1 is equal to 0, right? All for this to become a trivial solution is when c2 becomes 0. So now let's check. So if I look at this, right, for when y is, let's assume we are to get a trivial solution, right? Let's assume we want to get a trivial solution. So which means that c2 will be 0. But for y to be equal to 0, either c2 or this here should be 0, right? For y to be equal to 0, and remember this sum multiplying each other, either this or this would be 0. So let's assume we don't want to get a trivial solution, right? Let's assume we don't want to make c2 to be equal to 0. Let's assume we want to make this one to be equal to 0. So can we make this to be equal to 0? Let's look at this. This is shine, right, of lambda 5. Now what can we do right here to make shine to be equal to 0? Which is nothing. We cannot make shine to be equal to 0. If you can remember, my shine of x is exponential x plus x minus x divided by 2, right? Now what can we do to make shine x to be equal to 0? Which is absolutely nothing. There's nothing we can do to make shine x to be equal to 0. Definitely means there's nothing we can do to make this to be equal to 0. So since there's nothing we can do to make that to be equal to 0, we have no choice but to make c2 equal to 0. So since we make c2 to be equal to 0, my y is 0. So which means y is a trivial solution. So it means we obtain a trivial solution when lambda is less than 0, and also obtain a trivial solution when lambda is equal to 0. Right. So all that is left for us right now is for our third case, which means when lambda is greater. Now let's go to our third case, which is when case 3, which is when lambda is greater than 0, right? So remember, we can apply our Sturm-Liouville equation, given this is y double prime plus lambda y equals 0, right? So when lambda is greater than 0, we'll be having this plus lambda, right? So we don't need to change it, so we can just solve from there. So applying our auxiliary equation, we'll be having m squared plus lambda equals 0, right? So solving, okay, before we solve this, we all know that this also means d square y dx square plus lambda y equals 0, right? So now if you can remember our second order solution to second order equation, which is of this form, the solution we'll get will be y equals exponential alpha x open bracket c1 cos beta x plus c2 sine beta x. So this is the solution we'll get, right? So instead of, we don't need to solve it, right? So going from here, m squared plus lambda, we'll be having, now if I compare these two equations, I know that lambda is equal to n squared, right? And which means n is equal to the square root of lambda. So I don't actually need to solve it. I'll just take my stuff from here into the equation. So my y becomes my alpha. Now if you can remember, okay, now let's actually solve it. Now let's take this to the other side, right? So this m squared equals minus lambda, right? So square root in both sides, my m is equal to plus or minus lambda, right? Remember, the square root of this right now becomes plus or minus, this is my complex number sign, right? Square root of lambda, right? Remember, square root of this, of any negative number, gives you a complex number, right? And where my j there is my complex number. So now remember, our general form of complex number is usually the real number plus the imaginary number, right? But in this case, we only have the imaginary number. We're only having this, right? We don't have a, which means my alpha here is equal to 0. So this alpha is standing for the alpha in the solution right here, and my beta here is standing for my complex number, which is my square root of j. So let's just substitute it back into our solution. General solution will be having exponential alpha 0 x c1 cos my beta here is square root of j of lambda, right? Square root of lambda x plus c2 sine square root of lambda x. That's that. So writing my solution of y, this gives me c1 cos lambda x plus c2 sine lambda x. Right. So now let's proceed using our boundary condition, right? Where y as a function of 0 is equal to 0, and where y as a function of 5 is equal to 5. So which means this is x is equal to 0, and this is when x equals to 5, right? So substitute in our equation. Let's test for when x is equal to 0. When x is equal to 0, when I put it here, y is equal to c1 cos, this definitely gives me 0. Then this is c2 sine, this definitely gives me 0, right? So cos 0 is 1 and sine 0 is 0. So my c1, my y is equal to c1, right? And since y is equal to c1 and y is equal to 0, which means c2, which means c1 is equal to what? 0. As easy as that. So solving for my second boundary condition, for which s is equal to 5. Substituting in my form, since I have c1 to be equal to 0, I don't need this aspect of the formula. I just need this one. So y is equal to c2 sine square root of lambda x. So which will test for when x equals to 5, right? So this is this is y is equal to c2 sine lambda x times 5, right? So now before we go ahead, like I said, this is our since we've already gotten trivial solutions for lambda is equal to 0, lambda is less than 0, definitely we must actually get the eigenvalues and the eigenfunction of this one, right? So that we will not actually get a trivial solution again, since we already know that for when lambda is less than 0 is a trivial solution, equal to 0 is a trivial solution. Let's check if this will also give us a trivial solution. So now let's assume that we want to get a trivial solution, right? So for us to get a trivial solution, c2 will be 0, right? We only need c2 to be 0. Only need c2 to be 0. So in order for y to be equal to 0, we know that c2 will be 0, and also this will be 0. Either this is 0 or this is 0, right? Let me repeat myself. For an equation to be 0, and we have two variables multiplying each other, is either one of them will be 0. Just like when I have y is equal to x times z is equal to 0. So what made y to be equal to 0 is either x or z, right? So if x is 0, this becomes 0. If z is 0, that's also 0, right? So for this to be 0, either c2 or this will make it 0. So but we cannot use c2 to be equal to 0. If we use c2 to be equal to 0, it gives us a trivial solution, which means c1 and c2 is 0, and it gives us a trivial solution. But since we cannot use c2 to be equal to 0, let's take this to be equal to 0, right? Leaving out c2. So sine lambda times 5 to be equal to 0. So now you're going to be looking for values you can have to make sine of this to be equal to 0. So what are the possible values that makes sine functions to be equal to 0, right? What are the possible values that can make sine functions to be equal to 0? Right. So for example, I'm having something like this, right? So for example, I'm having something like this. So now for the possible values of, recall that sine x is, for example, if sine x is equal to 0, what made sine x to be equal to 0? What are the possible values that you think that make sine x to be equal to 0? We have pi. Pi is 90, right? Sine 90 is also equal to 0. We have 2 pi. 2 pi is 180. And sine 180, does it actually give me 0? Let me check. Sine 2 times 180. Sorry, sine 2 times. So pi is 180, not 90. So times 2 times 180 does not give me 0, right? Sorry. So pi, which is 180 sine 180 is 0, right? 2 pi, which is 360, also gives me 0. So this, I'm trying to get the possible values that can make a sine function to be equal to 0, right? So you see there are possible values that can make sine function to be equal to 0. So if that there is no possible values that we can apply to this that can make a sine function to be equal to 0, then we move on to assume c2 to be equal to 0, and which gives us a trivial solution. But since we can have possible values that can make a sine function to be equal to 0, we can work with that. So going back to this right now, so values that can make a sine function to be equal to 0, we'll assume that if lambda is equal to pi or 2 pi, right? It's going on and so on and so on and so forth. Be going on like that, right? Do you understand what I'm trying to do here? So if lambda is equal to pi or 2 pi, then let's test for 3 pi. 3 pi, which is 3 times 180, right? So sine 3 times 180 also gives me 0. So we'll be going on like that and like that. 4 pi. So if you notice that going higher and higher when lambda is replaced with pi, going on and higher, you see that sine is always equal to 0. So which means that 5, taking this 5 square root of lambda is equal to n pi. That means the sine function of this is equal to 0. You understand what I'm trying to say? So we tested that what are the possible values that can make a sine function to be equal to 0, and we had pi, 2 pi, 3 pi, 4 pi that can make a sine function to be equal to 0. So taking this right here, values that can make this, remember this is represented as x, so values that can make a sine function to be equal to 0 will be gotten from this place, right? So this is 5 times lambda, and 5 times lambda are the possible values that will make a sine function to be equal to 0, which is also equal to pi, 2 pi, 3 pi, 4 pi. So since we are having consecutive numbers here, 1, 2, 3, 4 and 5, let's represent it as n, where n is starting from 1, 2 and so on and so forth, right? Where n is starting from 0 actually, because you know that sine of 0 is also 0. So solving this now this is what we need. We've already derived the relationship between sine function and the function of y we have. So now let's square it to both sides. This is 5 root pi. Remember, we are looking for the eigenvalue. This right here, like I said, lambda is presented as my eigenvalue. So we are looking for this value of lambda here, and we are looking for the value of lambda in which we will not have a trivial solution. So since we can't have a trivial solution where c2, we assume c2 to not be equal to 0, right? So we'll be solving this is n pi, right? Square rooting both sides, square rooting both sides. So this is 25, right? Times lambda times n square pi square, right? Divide both sides by 25. Divide both sides by 25. My lambda is equal to n square pi square divided by 25, which can also be written as n pi over 5 all squared. So this is my eigenvalue to have, which we use to find the lambda, the original solution actually, which was y is equal to c2 sine square root of lambda x, right? Before we substituted when x is equal to 5 to get our value of to get our eigenvalues, right? This was the original second solution we had. So now substituting the value of lambda, we had c2, we have a c2 sine, if this is square root of lambda and this is lambda, so this gives me n pi over 5 times x, because square root will cancel the square up here. So this gives me y is equal to c2 sine n pi x over 5. So this right here is called my eigen function. So thank you guys for watching, and please do so well to subscribe. So like I said, these are all what we need in a Sturm liouville problem. We need to find the eigenvalue and the eigenfunctions. Thank you guys for watching, and please hit the like button and subscribe. So on our next video, I'm going to be treating another example. So see you on the next video.